How you doing? I'm Mr. Rose, and today we're going to go over a practice problem out of the text Young and Freeman's 13th edition, University Physics. The question that we're going to go over is in Chapter 2. It is question 2.62 in Chapter 2. So, this question gives you a graph, and the graph, I'm just going to sketch it out a little bit here. The graph looks something like that. And the graph has an axis of acceleration versus time, and it doesn't start at 0. Our increments, this starts at 2 seconds, is a y-intercept at 2 seconds, and we have a 1, a 2, a 3, looks something like that. Now the question has two parts, part A and part B. Part A is we want to find the stone's velocity at two different times. Time equals 2.5 seconds. And a time of 7.5 seconds. And then part B is sketching the graph that goes along with it, sketching a velocity versus time graph. So there are two methods to do this. The first method is just we do a little bit of dimension analysis and recognize that a graph of acceleration versus time, this was in centimeters per second squared, and time was in seconds, that if I take some simple area under the curve of my two shapes, I would have for part A, and again, I just have a sketch here. So part A, I would have at a time of 2.5 seconds, we'd have to estimate. I would say my small triangle, 1/2 base times height, plus the rectangle of just base times the height. Now, when I throw in my estimated numbers again, definitely look at the textbook so you have the exact numbers. You'd have something like 1/2, looking at my textbook, the base is in seconds, well, that is easy. That's my 2.5 seconds, times the height. And the height is really what you would have to estimate. And I estimated that at about 1.8, about 1.8 meters per second squared. And then we do the same thing, plus base times height. Again, my base would be 2.5 seconds, and my height would be about 2 centimeters per second squared. And we would add that together, we get something about 7.25 meters per second squared. Now that's one way to do it, which again is a little bit of simple practice calculus. Now there is a second way to do it, and it's a little bit more elegant, if I were to say so myself. So that second way to do it is recognizing what we have here. They gave us, well, if I go back to my sketch, let's bring that down a little bit. They gave us a y-intercept, or they gave us an acceleration at time equals 0. And we know straight from my graph that that is 2.0 meters per second squared. No estimation needed for that. Now, reading my graph, I'm going to look at, and now I'm going to say an acceleration at, reading my graph, off of the book obviously, at 2.5 seconds, I can read that to be 3.8 meters per second squared. And then at that second time, my acceleration, 7.5 seconds, I can read that as 7.5 meters per second squared. Now again, these are kind of just estimating, and we should recognize we know things about some graphs. We know what the slope of a distance time graph is. We know what the slope of an acceleration, a velocity versus time graph. Well, an acceleration versus time graph, the slope of an acceleration versus time graph yields something that is called a jerk. And a jerk is an acceleration of an acceleration, or more specifically, it is the rate of change of an acceleration. Well, we should know something about rates of change. So if I know that acceleration is a rate of change of acceleration, that means I can have an acceleration, a change in acceleration per change in time. Well, that seems like I could just say something like 7.5 minus 3.8, all in meters per second squared, divided by, I'm just taking a slope here, divided by my 7.5 minus 2.5 seconds, and that would yield, grab my calculator, 7.5 minus 3.8, divide that by 7.5 minus 2.5. That would yield something along the lines of 0.74 meters per second cubed. Now that meters per second cubed, again, that is my jerk. So now we want to relate that to some acceleration, right? My acceleration, so I want to relate that, to my initial acceleration to find out how fast I'm going at some specific time, right? So acceleration is equal to my initial acceleration plus my rate of change, my delta A divided by delta T at some specific time T. So what is that going to look for? That's going to look as A is equal to my initial acceleration, 2.0 centimeters per second squared, read that straight from my graph, plus 0.74, sorry, that says meters, this should be centimeters per second cubed. All of that at some time function t. Well, now what do we do with that? If I want to go from acceleration to velocity, what am I going to do? I know my velocity with respect to time, v naught t plus some antiderivative from 0 to some time t of my acceleration per unit time, ADT. This should look a little bit familiar to us at this point in time. Move my paper up a little bit. So now from here, what am I going to do? I'm going to take my antiderivative because acceleration is changing per unit time. So I know my velocity at some time t, my initial velocity times time, that has nothing to do with it, but my acceleration per unit time, ADT, hey, wait a second, that seems like something I just did. ADT, that is times the antiderivative of 2.0 centimeters per second squared, which is just some constant, plus 0.74 centimeters per second cubed times t dt. So now I'm going to rearrange this just a little bit, and by rearrange I apologize. I'm going to take my antiderivative. V of t is equal to v naught t, nothing happened there. My antiderivative from 0 to t of 2.0 is just plus 2.0 t plus 0.74 times t is going to be 0.74 t squared over 2. Now I'm going to rearrange that. So it should look familiar. Ready for this? V of t is equal to v naught t plus 2t plus 1/2 0.74 t squared. Is this looking at all familiar to us right now? I could rearrange this, v naught t plus 1/2 at squared. That should look a little bit familiar, right? So now at this point in time, I can just go and plug in my values. I could say v at 2.5 seconds is equal to 2.0 times t, 2.5. Sorry, messed that up. Try that one more time. No, I was right the first time. Not making a mistake. Velocity at 2.5 seconds is equal to 2.0 times t, 2.5, plus 1/2 0.74 times 2.5 squared. That looks right to me. Throw that into my calculator of 2 times 2.5 plus 1/2 times 0.74 times 2.5 squared. And that gets me the velocity at 2.5 seconds to be equal to 7.31 meters per second. Now, if I go back and check that against our initial estimate, you could see, doing our baby calculus right there, areas under the curve, antiderivatives, I estimate it to be about 7.25. So that shows that this works. Now, this is not what you have to do. You don't need to do it this way. It is an alternative approach, and as we get a little bit better, this calculus will feel a little bit more second nature. That's all I have for you today. Just that one simple example. Feel free to like, comment, or subscribe, and I will see you next time.